Instead of your worker asking Temporal for work, Temporal wakes your worker up when work arrives.
So your worker wakes up, it processes the work, and then it goes back to sleep. And when there's no work to do, there's no worker running. And no running worker means zero cost.
Hi everybody, welcome back to another video. My name is Melissa Herrera. I'm a dev advocate here at Temporal.
Hey everyone, I'm Ian Douglas. I'm also a dev advocate here at Temporal.
Hey everyone, I'm Manib. I'm an engineer on the team that built and launched Serverless Workers for you all.
If you were at Replay 2026, or you might have watched our keynote online, you saw Temporal just release Serverless Workers. We wanted to allow conference attendees to launch Serverless Workers through a voting mechanism. Our demo didn't go exactly as planned though.
Yeah, the nature of live demos and being dynamic enough to work around when things go sideways.
And so over the span of about 10 minutes in our demo, when people were sending in tens of thousands of votes, we processed those as temporal activities handled by serverless workers on AWS Lambda.
So every vote that conference attendees sent in contributed to that total tally of votes. And even when our hosting service went down briefly in the middle of it, Temporal kept working.
And today, we're going to share some of the charts of the voting results with you and spend time looking a little closer at the demo.
Okay, so let's start from the beginning. What actually is a serverless worker? With traditional Temporal, you run a worker process. It starts up, it connects to Temporal or Temporal Cloud, and it's pulling a task queue continuously asking, hey, you got any work for me? Over and over, whether or not there's work to do. It's running 24/7. You manage it and you pay for it even if it's not doing anything.
Serverless Workers flips that model completely. Instead of your worker asking Temporal for work, Temporal wakes your worker up when work arrives. You deploy your worker code to AWS Lambda, Temporal's worker controller instance, a system workflow that runs in your namespace, monitors your task queue. The moment tasks arrive and no worker is available, it then invokes your Lambda function directly.
So your worker wakes up, it processes the work, and then it goes back to sleep. And when there's no work to do, there's no worker running. And no running worker means zero cost.
Yep, and the best part of it all is that it's the same Temporal SDKs, same workflows, same activities. The only thing that changes is the lifecycle of your worker.
And you still own and run the code in your own environment. You are just passing a reference to your Lambda environment to Temporal, so we can wake up your Lambda workers on demand when there's work available.
So we showed a live demonstration of how this works during our keynote at Replay 2026. And if you haven't seen that YouTube video yet, we're going to watch a couple of clips of what we built.
So here, each attendee was able to scan this QR code, and it loaded up a web app that showed some emojis of our Ziggy mascot. They then pressed a button to vote, and that vote was sent to our system as a workflow activity. Each vote was one activity, one durable, tracked temporal native job.
And here, every vote triggered this exact sequence. Each emoji sent hit our temporal endpoint, which submitted as a temporal activity. Temporal checked if a Lambda was running or not busy and handled the activity to that worker. If a worker wasn't available, it spun up a new one.
And that happened simultaneously for thousands of votes. The moment the spike hit, Lambdas followed, almost instantly.
So here's a graph of what that voting looked like. And you'll notice that there's this big gap in the vote graph here where things slowed down. And that's when our hosting service for the voting app went down briefly. Maybe they should use Temporal too. But the votes that were already submitted didn't disappear. They stayed in the task queue backlog. And the moment that the service came back up, people could keep voting and everything kind of continued as normal. These other graphs that we built out here basically showing which emojis were voted on. And then here was kind of this cumulative total. And we can see this plateau here was when the voting app went down. And by the time all the voting finished, you can see at the top of this box here, we were right around the 60,000 vote mark. And we're going to talk a little bit more about the fire emoji that won and what the implication of that was.
Okay.
So every vote was one temporal workflow. On our voting app screen, we showed numbers at the top of the screen for how many votes were queued and processed. You'll see these up here at the very top of the screen. Processed means that the workflow completed successfully. Pending means it was still running, but crashed means that a Lambda invocation failed abnormally.
And as Ian was just alluding to, we chose a special emoji designed to crash Lambda workers on purpose, the fire emoji. And with a coin toss, it would either exit cleanly or exit abnormally.
And when that happened, Temporal detected the failure. It scheduled a retry on a fresh Lambda invocation, And that invocation eventually succeeded. Those crashed numbers aren't lost votes. They're actually votes that failed and got retried automatically.
And from a worker's perspective, before voting opened, you'd see roughly one worker running on our laptop. At peak during the spike, Manib is going to show us exactly what that looked like. But after voting closed and the Lambdas finished their work, they eventually all spun back down to 0.
So this is the part I want to really dig into. Here's the real Lambda concurrency graph from the demo. What you're looking at is the actual number of Lambda invocations running simultaneously over the course of the voting window. The moment the voting started, look at that spike. That's real. That's hundreds of votes hitting our server every few seconds from the audience. At peak, we had about 16,000 Lambda workers for the aggregated 60,000 votes that Ian just covered. So let's look at how these relate to each other. The reason for that is that we had configured a 1-minute timeout for each Lambda worker. So each Lambda worker stayed awake for 1 minute and processed as many votes as it could during that window before shutting down. And if a vote it was processing was the fire emoji, then the worker was doing the coin flip to either crash or exit gracefully, in which case it would have restarted the worker and finished submitting the vote. And here's what that cost us. 60,000 total votes processed, around 16,000 Lambda workers were invoked, and the total cost was less than $3.
And that's pretty awesome. I mean, compare that to running a fleet of workers 24/7 at the capacity you'd need to handle that kind of spike. You'd be paying for that capacity every single day, whether you'd have a Keynote demo happening or not. And with serverless workers, you pay for the spike when it happens. The rest of the time, you pay nothing.
And here's my favorite part of this graph. After voting closed, we still had some coin flips to process, which sometimes continued to launch new workers, but everything settled in about 15 minutes. No more workers, no more cost.
Yeah, I love this. No one had to write a scale down script. No one had to set up a CloudWatch alarm to terminate instances or anything like that. Temporal and Lambda just stopped when the work was done.
All right, let's add a bit more context to what Ian and I were saying here on stage. 3 things make serverless workers genuinely different from workers that you just host yourself. First, as we saw, they scale to 0. So when there's no work, there are no workers. For workloads that are spiky or unpredictable, like AI agents, event-driven pipelines, or an audience voting at a conference, this changes the economics completely.
Second, there's no infrastructure management. You don't have to set up infrastructure where your workers run. You don't have to manage Kubernetes. You just write your worker code, you deploy it to Lambda, you do a little bit of configuration, and then Temporal handles the rest. Your mental model now goes from managing your workers to just writing code.
And third, it's still Temporal underneath it all. Every workflow is durable. Every activity has retry semantics. Every failure is handled. Each vote that crashed because of the fire emoji was retried automatically. None of that required any manual intervention. That's not just serverless though. That's serverless with Temporal's durability guarantees on top.
So if you're building something with unpredictable traffic, whether it's AI agents, event processing, or anything that spikes, serverless workers is worth a serious look.
And at the time of recording this video, serverless workers is currently in pre-release, so the APIs are still evolving. But the core capability is there and it's ready to experiment with.
And if you want to dig into the AWS side, the Lambda configuration, the IAM setup, how to tune your timeout for your specific workloads, there's a lot more detail in our official documentation. We are also happy to help answer any questions in the community Slack too.
We're going to make links available to all these things down below, along with the full Keynote video so you can watch the whole demo in context.
Thanks so much for watching, and we'll see you in the next one.
Bye.
Bye, everyone.